Okay, so let's say, suppose that we have, okay, we take the same example, the swing. We have three positions, right? We take one is the negative displacement, put it negative R, maximum amplitude, and zero amplitude, and we have positive amplitude. We first look at to draw the energy graph. Okay, we kind of drew an axis for the energy against displacement graph, right? So we have displacement is the x-axis and energy is the y-axis. So I'm going to put, because I got positive and negative displacement, so here is positive R, here I would put negative R, and let's observe what happens to the kinetic energy at these 3 points. At the negative amplitude, the kinetic energy, because this is the turning point, so the turning point is where the object stops temporarily. So the V would be 0 here. So I'm going to write, okay, let's just put down a point. V is 0. So that means kinetic energy is 0. Okay, 0 here. And then at the equilibrium position, kinetic energy is maximum, right? So over here. And at the other side, the other extreme, it is also 0. So let's connect the dots. We connect it, we get a curved graph like this. Okay, so this shows our kinetic energy graph against the amplitude graph. Okay, it max at the equilibrium positions. Now, what about the potential energy? Potential energy is the opposite of kinetic energy. So if we take the negative R, at this point is where it is at its highest position, right? There are two instances where it is at highest position. So negative R and R. So that is when the potential energy is maximum. So if we are talking about pendulum, so that's height. If you are talking about like a mass and a spring, okay, then we are talking about like elastic potential energy. Okay, elastic potential energy. You have many, many types of oscillating system, right? So for this one, I would just say, okay, at here, energy is the maximum, the potential energy here. And then at the equilibrium position is where no potential energy, and same here, it is up here. So we connect the dots again, we get a curved graph like this. Like this. Okay. Now, here, this is EP, is EK. If we look at any time, at any point in time, let's say we just take a random here. This one, the EP plus the EK at this specific point in time, we add it, we get the total energy. Okay, we do it for every single point on the curve, we get the total energy is the same. This one is the total for this one plus this one. And if we take the point over here, again, we take how much is the EP, how much is the EK, we add up the height, we get the total height here. If you do that for every single point, you will get a straight line that represents the total energy. Okay, so the total energy, what energy is this one? This is mechanical, right? Mechanical is a combination of potential and kinetic. So I'll just label it E total. It's constant. So the total energy of the oscillating system does not change, it's constant, assuming that if there's no energy loss. Okay, so in the question, in the past years, in the exercises, always they will ask you, okay, what is the total energy? They'll ask you to find the total energy. Now, a few things, if you want to find the total energy, you can find it from the potential or you can find it from the kinetic. So at the potential, you know that at the maximum displacement is where the potential is max. So that means at here, the potential energy equals to the total energy. So all you need to do is find what is the potential energy at here, then you know the total energy. So if it's a pendulum, then you can do like mgh, you can find the total energy. But more commonly, we would use the kinetic energy to find the total energy. So let's say we would take what is the kinetic energy at the equilibrium position at the center here. This is where EK is max, and that is equals to the total energy. How do I get max EK, kinetic energy? We know kinetic energy half mv squared, depends on the velocity, right? So if the velocity is a maximum velocity, then I get kinetic energy max. So half mv max squared. From the previous lessons, if you remember, I gave you a table of all the formulas. If you look at that one, V max equals to what? V max equals to omega R. Okay, R is amplitude. Okay, sometimes you see your book, they use A, it's the same thing. So omega R, we put it in the equations, we get EK max equals to half and m omega square R square. Okay, so this is to find the maximum kinetic energy. If you know the omega, which is a constant, and if you know the maximum amplitude, then you can find the maximum kinetic energy. That equals to the total energy as well. Okay, so usually we find the total energy from the kinetic energy or the potential energy. Why the graph is curved? Why the graph is a curved graph is because you see kinetic energy is proportional to velocity, right? And you know that velocity is proportional to displacement. So that means kinetic energy is also proportional to displacement, square, because you have a square here. Okay, so that's how you get this curved graph of the kinetic energy as you plot the kinetic or the energy against the displacement graph. And also other type of graph is also you need to know how to draw the energy against time. Okay, so let's say we take the same example, swing. We would call this point A, point B, and point C. But let's say I swing from point A. Okay, I swing from point A to point B here. Now I'm going to create a kinetic energy graph. This is EK, and this is time. So kinetic energy against time. From here, starting from A, kinetic energy is 0. Okay, swings to B, that is the maximum. B is the maximum speed, so you have maximum kinetic energy. This is from A to B. Okay, and then from B to C, decreases to 0 again. So the graph curves back down, 0. And then you swing backwards from C to B, increases again. Because energy is a scalar, right? It's a scalar quantity, so it doesn't have a sign. So I will just draw everything on above the x-axis. So this one stays above and increases to maximum again. And finally, from B, swing to A, decrease again down here. Okay, let's stop here. Let's stop here, and then you see we have swing from AB, BC, CB, and BA back to starting position. That means there's one period. Okay, one complete oscillation. Now, from here to here, the energy graph from here to here is one complete oscillation, one period. Okay, that means the kinetic energy goes through 2 cycles during one period of oscillation. Okay, you have 2 cycles of the graph in one period of oscillations. Okay, so if you draw the rest, it's the same, just repeating this one, then this. Right, so this is the kinetic energy against time. All right, what about the potential? Potential is just the opposite of kinetic energy. So if I draw it on the same axis, potential would be like this. When the kinetic energy tops, the potential energy becomes minimum, like this. Okay, like this. Yeah, it's the opposite of it. Okay, sorry about this one. Let me draw it on a separate graph. EP, okay, and started at first is maximum, right? So maximum 0, maximum 0, maximum 0, maximum 0, maximum. Right. Okay, like this. Okay, this is the opposite of kinetic energy. So as long as they add up to the same total energy, total energy would be straight line. So if I have a graph of E total against time, straight line graph, constant. Okay. Okay, now is the energy, the total energy in the system always the same? It depends on whether there is a damping happen to the system or not. Okay, what is damping? We'll talk about damping, which is loss of energy in an oscillation. The total energy of the system will decrease if there is a damping. Now, for example, let's take a pendulum, right? A pendulum. Now, I displace the pendulum to 10 cm from the equilibrium positions, okay? And then I let go, let it vibrate. The pendulum swings back and forth, and at first it was 10 cm, then 9 cm, 8 cm, 7 cm, 6, 5, and then 2, 3, 1. Eventually, it stops. This is what we have seen in the actual case, right? So, object will not stop oscillating. Object will not stop oscillating unless there is an external force applied. Because we have understood inertia, so objects has no power to change its own state of motion if there's no external force. That means if the pendulum eventually they come to stop, that means there is an external force acting on the pendulum. Now, what is the external force and where does the external force come from? This external force is due to an object moving in a medium, in air or in water, it can be any medium. So whenever an object moves in a medium, there is a force, we call it the drag, right? So object is moving in this direction. There is a drag of air in the opposite directions. You have studied about this one. That is called what? That's called a viscous drag, right? In the earlier chapters, right? The viscous drag. So other than this drag, what else? What else are the external forces? So we have the viscous drag, we have the frictional force, okay? It can be the friction here and there, okay? The internal friction and everything. All these forces, they are called the damping forces, okay? Damping forces. They are considered the external forces. So what these forces does is that they take out energy from the system as heat. You see, when object moves in a medium, heat must be produced because of the drag. So drag creates heat. If you're talking about like a piston moving in oil, also there's a heat produced in the hydraulic oil. So it removes energy from the system as heat. So some of the kinetic energy will eventually be converted to heat energy. Okay, so since they are removing energy, that means the system loses energy as it oscillates. Over time, it loses energy. So for each oscillation, for every cycle, the amplitude goes on decreasing. Okay, the amplitude goes on decreasing. Now, if you plot the graph of amplitude against time, so we want to see what happened over time. as time increases, you see that the amplitude decreases exponentially. So let me draw it here. Let me clear this first. I'm going to clear this first. Right. So we have here, then we have like this. Now, the first oscillation, the first period, you have like this, and then eventually it decreases like this. If you connect the dots, the peak, you find that it is a curved line like this. It is a parabolic. Okay, this is a parabolic decrease. It is not a straight line. So this process of parabolic decrease in the amplitude, we call it the damping process. So this is damped oscillation due to external force, the viscous force. Now, viscous force depends on what? Depends on the speed, right? The velocity. The faster the object moves in the medium, the greater will be the drag. So we can say that the more the velocity, the more the damping. Okay, the more the movement of the object, the faster it moves, the higher will be the damping, the greater will be the damping. Okay, so we have a few types of damping. This one you see on the graph here. What is the behavior of the object? The object, is it still oscillating? Yes, it's still oscillating, right? But it oscillates with smaller and smaller amplitude. It doesn't just like stop suddenly. So it like tapers off over time. It subsides, okay, decreases over time gradually. So this type of damping, we call it light damping. Okay, light damping. Other words, sometimes you see like they call it the underdamp. Okay, light damping or underdamp. Example of light damping is like pendulum. Okay, like a spring mass or a pendulum, vibrating pendulum. Okay, all these are light damping. And other than light damping, we actually have a stronger one. We call it the critical damping. Critical damping. Sometimes you'll see over damping also. Okay, over damping. Just like increase in the magnitude of the damping lah. Okay, so over that actually it's light damping first, comes and then over damping and then critical damping. So if you draw the critical damping, the graph would be like started with the amplitude, and then it decreases like this, decreases like very sharp decrease. Okay, the decrease in the amplitude happened in a very short time. That means you don't see a sine curve or a cos curve like this, right? That means that the object is not oscillating. In critical damping, object, they do not oscillate. They initially vibrate, and when they undergo critical damping, then they will come to stop in a very short period of time, instead of vibrating like the pendulum, slowly vibrate and then stop. But the similarity between these two is that eventually they will come to a stop. Okay, just that this one happened faster. So this is critical damping, and actually you have more than that. You have like another one that is a stretch out longer. What's the difference between this one? It's just this one happened for a longer period. Okay, so this is like over damp. This is light damping, and this is critical damp. Okay, this is critical damping. It's all due to the external forces. External forces. What is an example of a critical damp? Okay, in real life, what is the example of critical damp? It's like the car suspension system. Okay, when a car runs over a bump, there is a shock to the car that causes the car to vibrate up and down. Okay, when it runs over a bump, so it goes up and down. Now, in front of the car, just under the hood, there are a few dampers that we call it the shock absorbers, right? So what are shock absorbers actually? The main component of a shock absorber is like this. You see, it's like a tube Okay, under the hood of the car, there's this tube that is fully filled with oil, hydraulic oil, yes, fully filled with hydraulic oil, and then there's a piston inside, right? And this piston, there's a shaft connected to a shaft, like a rod, and then outside here, you have a spring. Okay, you have a spring like this. This is just the main structure of the absorber. Okay, so the top one goes to the body of the car. Okay, it's attached to the body of the car, and then the bottom one goes to the wheel. Okay, goes to the wheel. So this thing, we call it the dampers. Okay, the shock absorbers. What does it do? It gives, okay, when there's a shock, okay, when there's a shock, it damps over time because of this shock absorber. How it works is that when there's a shock to the car, it causes the car to compress the piston. Okay, so whatever happening, shaking, compression happen to the car, it will get transferred to the piston. Okay, it get transferred to the piston, and then the piston will move up and down, compress, because this one is fully filled with oil, right? You have oil here at the back, oil here. So as the piston push down, some of the oil will move to the back of the piston. That means it will squeeze the oil, and then the oil will move here. Move here, move to the back, move through the piston, goes to the back. Okay, and then same happen when the piston rebound. When the piston retract because of the string, the spring, and then the oil will go back to the original position also. So it's kind of like the oil go left and right, left and right. So what does this do is that it kind of extract the energy away from the vibrating piston. Okay, it extracts energy gradually, okay, away for each stroke. When it goes down, this kinetic energy of the piston, okay, pushes the oil, and then it will heat up a bit. Temperature will rise. It creates friction. Again, that's viscous drag. So there's friction, there's heat. So energy is extracted out in the form of heat for one stroke. You stroke down, okay, energy loss. And then when you go up, same, because the oil comes to the other side, right? So when you retract the piston, again, there's this friction with the oil here. So the thing is, you have to make sure that this piston is like completely filled with oil all the time. Okay. So actually, the piston got like a hollow part lah. Okay, the oil can flow through. Okay, because we don't want to be like a fixed object. There's a cut section in the piston so that when you compress, you don't create like too much force on one side. Okay, something like that. Okay, so the key point is that when the piston vibrate, then it's going to be converted to heat energy, and that's how the engineers, the scientists, they use damping. Okay, they use the damper, okay, to bring down the amplitude of the vibration. So like a car running over a bump or anything, it vibrates. So we want to bring it down to equilibrium in the shortest time possible. Otherwise, your car is like bouncy like this. Okay, we don't want that to happen. All right. So that's damping, one of the real life application of damping. So in a car, it's like critical damping. Okay. Right. Now, other than the damp oscillation, is there a case where the amplitude can remain the same? This one amplitude decreases over time, right? Yes. So yes, there's another scenario where amplitude remain the same, does not decrease. So if we sketch the graph, amplitude against time, this one also amplitude against time. It's like this. Okay, same amplitude. This is like what? This is like a clock. Okay, inside the clock, there's energy loss, yes, but the energy loss is made up by the battery, the spring, anything that we design to drive the clock. Okay, so the energy loss is compensated by other forces in the clock so that it maintains to vibrate at the constant amplitude. So this one, we call it undamped. Undamped oscillation. Example, like a clock, a metronome. Okay, a metronome where it ticks back and forth at the same period, doesn't decrease in amplitude. Okay, so all these are examples. Now for undamped oscillations, you can kind of have two types, right? First is like, imagine like you vibrate a spring, you vibrate a pendulum in outer space. Okay, so there's no energy loss. That is also undamped. Or it can be like what I mentioned, the clock, where you use external forces to maintain the amplitude. That is also undamped. What is the difference between that two? One is free oscillation. For the amplitude, I let it vibrate. If there's no energy loss, there's undamped, but that is free oscillations because I'm not applying any external force to drive it. But for the clock, there's a force oscillation because I am applying external force to keep it undamped. Okay, so we have two types of oscillation. Again, free oscillation and force oscillation. Okay, what are these two things? Let's see. Let's start with free oscillation. Take the same example, the pendulum. Okay, now I displace it to the side and then I let go. So it vibrates left, right, left, right. I'm not touching it. I let it vibrate freely, okay, with no external forces. That is called free oscillations. That means oscillations under no influence of external forces. Now, when I let go of the string, right, of the pendulum, I just let it do whatever it wants. And then the frequency, what is the frequency that it makes? What's frequency again? Number of cycle in 1 second, okay? How many cycle per time? So what is the frequency of the pendulum? Depending on a few factors. Like what? The length of the string, the length of the pendulum, the mass of the pendulum, okay? We actually have a formula for that, right? So there's other physical, there are other factors, other physical quantities that will decide. It will decide what frequency that the string will vibrate at, the pendulum. That frequency is called the natural frequency. Okay, now understand what is natural frequency. Natural frequency is the frequency of a vibrating system when it is allowed to oscillate freely. So free oscillation. It depends on what? It depends on the length, it depends on the mass per unit length of the string, many factors that define what is the natural frequency of the system, of the vibrating system. Okay, so for example, I let go of the pendulum and then I observe, I calculate, okay, what is the frequency of this? Okay, let's say it does like 20 cycle in 1 minute. 20 cycle in 1 minute, that means the frequency is 20 oscillation per minute, right? Okay, so 20 oscillation per minute. Now, what if I suddenly do this? I hold it and I vibrate it like this. Okay, my paper keeps flying around. Wait. I hold it and then I vibrate like this. So what is this? This is I'm applying a force, right? First, I'm applying a force, and this is called a force oscillation because I'm disturbing the system by applying a force. Now, if you observe that this force that I apply, it is actually an oscillating force. What do I mean by that is that not only the system is oscillating, but the force is also oscillating. Here, I apply to the right. When it comes here, I pull it back to the left. When it comes here, I apply to the right. So it's like It's like simple harmonic motion. Even the force behave like simple harmonic motion. So we call this oscillating force, right? The oscillating force, that means that the force is continuous, is periodic. Okay? Now, what happened to the system then? The system, the pendulum, will follow the frequency of the oscillating force. Now, you see, in force oscillation, okay, in force oscillation, I apply a force that we call it the driving force. Okay, the driving force. And this driving force, because it's oscillating, that means it has its own frequency as well. We call it the driving frequency. Okay, the driving frequency. The pendulum will oscillate at the same frequency as the driving frequency. Initially, it was vibrating at 20 cycles per minute. Now I hold it, I vibrate like this, and my force, my driving force, the frequency of my driving force is 30 per minute. Now the system vibrates at 30 because I'm forcing it to vibrate at 30 per minute. And then I change again. Now I increase my force. 40 per minute. What happened to the system? The system also vibrates at 40 oscillation per minute. So it always follows the frequency of the driving force. Okay, so that is force oscillation. I'm not allowing it to vibrate freely. I'm forcing it at a certain frequency that I want. Okay, so that's the difference between free and force oscillations. How do we define it? Free oscillation, you just put it simply like this. Free oscillation is oscillation under no external influence. Okay, force oscillation. Force oscillation is oscillation under effect of oscillating force. And actually, this one has an equation as well. The force, the oscillating force has an equation. We can write it as F equals to F naught. That's the maximum force, just like maximum displacement. Cos omega d, that's the driving frequency time. Okay, now you see, in free oscillation, we have studied the equations. Very simple equations, the simple harmonic one. X equals to amplitude cos omega time. Okay, this is the vibration of the pendulum of the system. And for force oscillation, because I am applying a force to vibrate it, so this one become this one. X equals R. Okay, this one is still the same, the maximum amplitude, and R cos, and the frequency, the omega, become the driving frequency time, and then we plus this angle. What is this? This is actually the phase difference. The phase difference created between the force oscillation and its natural vibration frequency. Okay, you may have seen this formula. Actually, it's the same as this one. Okay, just that we added the omega instead of the omega natural is the omega of the driving force, and plus the phase angle, the phase difference in terms of angle. Okay. See, so we have two types of free oscillation and force oscillation. Two types. If we are talking about the free one, the free oscillation, sometimes there can be no damping. In what case? Free oscillation, no damping is like when there's no, like you do the experiment in space, something like that. No other frictional external forces, so there's no damping. Okay, and also free oscillation in the real life, in actual case, yes, there's damping. Okay, that's damping, just like a pendulum vibrating, eventually it will stop. And force oscillation, also we can have no damping, just like the metronome, we force it to vibrate at the same amplitude. So total energy is still the same because the energy that I put in and the energy that is lost is equal. So that is the same. No damping, force oscillation. And force oscillation can also have damping. That is like the car absorber system, the car suspension system, or like the bridge. They use the damper to prevent resonance happen in the vibrating bridge. Okay. Okay, so why do we need damping? The main thing is that to prevent resonance happens. Okay, now let me erase this. I'm going to go to the new slide. What is resonance? I always tell people that you think of resonance as this one, like a person taking a swing. You swing from the right to the left. Here. There's a person pushing you at the back. Now let's say that you swing one cycle. That means that you started here at point A, you started here, and you swing, come back to the same position. You take 3 seconds, let's say 3 seconds. Okay, so your frequency, okay, 3 seconds, 1 vibration. Okay, that is your frequency. And there's another person pushing you here. He applies a force, and this force is not one time, it's periodic. So that means, in other words, it's oscillating. Okay, it's continuous. So depending on what is the frequency of the force. Now, remember, we got 2 frequencies here. One is the frequency of the vibrating swing. Another one is the frequency of the force. Okay, that means how fast the force is applied between the first force and the subsequent one. Okay, what is the time period between? So let's say that this guy, this person, he applies a force that has a frequency same as the swing. That's same as the frequency of the swing. So that means that every 3 seconds, push 1 time. Push once every 3 seconds. You see, you started here, every 3 seconds you come back. And the force also oscillating. The force is oscillating like every 3 seconds, push 1 time. Okay, so that means the force acts every time when you are back at the original position, and every time when you're about to swing, right? When you're about to swing, the force acts. So that means this is when the frequency of the force is the same as the frequency of the system. Okay, 3 seconds, 1 vibration system. What happens when the frequency of the force is the same this one? Okay, you can already expect what to happen. The height increases. The height of the swing, you can swing higher. The amplitude increases. You can also do this by yourself, right? So you can do like every time you swing to the highest position, what you do here, you swing your leg. You can increase your altitude a little bit more by swinging your leg forward every time you're at the highest position. And every time you're at the lowest position, you swing your leg backward a bit. You can increase your height slightly. Same, you keep doing it. What happened? What you are doing? You are, again, applying an oscillating force. That force is periodic. Every time you come here, you apply. Every time you come here, you apply. And that force happened to be in time, in tune, match with the frequency of the system. So result is resonance. So the amplitude become higher, increases in height. Okay, so that is resonance. So resonance, how do we prevent it? What is the danger of resonance in the previous physics that you study in high school? There are many incidents happen, like the one back in 19th century, 18th century, I think it's 18 something. There was a bridge in England. I forgot what's the name already. That the bridge, there are 200 French soldiers cross the bridge. Okay, 200 French soldiers cross the bridge and they march when they cross it. And when they march, right, the footstep, all their footsteps are in unison, same time. So that means that the force from the footstep, okay, is oscillating also, right? So it has a frequency. That frequency, unfortunately, just happened to match with the natural frequency of the bridge. So that means that even though a small force, right, very small force, but they are in unison, they are like together, slowly it builds over time. The amplitude builds up over time, and what happened then? The bridge collapsed, and all the soldiers, they fell down to the sea, right? So that is what happened back in those years, okay, where this is due to what? Due to resonance. Is because of the oscillating force has the same frequency as the vibrating objects. Okay, and other bridge, there are few cases, other bridge also collapsed due to the wind movement. The wind movement, not very strong, but because the timing that it can crash the bridge. And there's just another one, like back in like 2000, where also in London, right? They just finished building the bridge. They just finished construction, and then they opened for public. And during the opening, all the crowds, they packed the bridge. Okay, all the crowds packed the bridge, and then what happened is that all the footsteps, okay, vibrates the bridge slightly, not many. Okay, but that incident, it was lucky, like it didn't collapse. Okay, it didn't collapse. But what happened is that because there are too many people, and then the frequency is very similar, okay, it's very close to the natural frequency, so it's kind of vibrate a bit, and then people just stumble and fell down. Okay, all these people, they fell down because of the bridge vibration. Okay, so now the thing is, resonance happens when what? When the frequency of force same as the system. Now in the we can say that, let's say this is the frequency, natural frequency. Okay, the closer you get to the natural frequency, I'm talking about the frequency of the force. If it's very close to the natural frequency, then the resonance, the amplitude will increase. The amplitude will be higher. The closer you get to the natural frequency, the higher is the amplitude. The further you are away from the natural frequency, the smaller the amplitude. Okay, remember that. So if you are, even though it's not exactly the same, but it's very like close, still the amplitude will increase. Doesn't mean that you have to be exact, then the amplitude increase. No, still there's resonance, amplitude will increase. Though, so I mean, meaning that if you plot the graph, if you have a graph of amplitude against frequency, okay, let me show you here. Let me open this one. Give me a sec. This graph sometimes will be asked in the exam also. Okay, yeah, this one. Okay, so what graph is this? See, amplitude against frequency. Okay, we plot this amplitude against frequency. Now, if you see, okay, I want you to focus on a few things. When you first look at it, like a bit overwhelming, right? You just focus on a few things. You see the vertical dotted line. This is the natural frequency. Okay, this is the natural frequency. Now, just now I said got a few types of damping, right? You've got light damping, you've got critical damping. Let's just look at light damping, the dotted line here, this one. Okay, let's just look at light damping. And what happened to the graph? You can see it looks like a mountain where it peaks at the center. And what happened at the center is like as it approaches the natural frequency. Okay, as the frequency of the force gets closer and closer to the natural, the dotted line, vertical dotted line, the amplitude rises. So that's why it peaks at the center here. And then it drops off here. Okay, so the further you are away from the natural frequency, the smaller the amplitude. The closer you are to it, the greater the amplitude. And it happens in all types of damping. You can see other types, you get no damping. Of course, no damping, the amplitude will be far greater than the damping one. Okay, so you have no damping, the light damping, critical damping, and overcritical damping. All this graph showing peak at the center. It's like all of them having a shape of a mountain. Okay, so this is where resonance happens. But the critical damping and the overcritical damping, you can see is a kind of different shape. But what happened here? Because the damping is too much. Okay, so that resonance cannot happen. The damping is too heavy. We say that the damping is too heavy, so that resonance cannot happen. Right? So you need to remember the shape of it, shape of the graph. Okay, so there's no resonance for the critical damping and the over critical damping. All right. And for the graph of damping, critical damping, and the over damping, we have another picture. Let me show you this one. Just now, because just now I drew not that clear, right? You can see this. Okay, so we have the light damping, like the pendulum, that goes through an exponential decrease. And we have critical damping, this one. You can see that there's no vibration, right? Critical damping, there's no vibration. So in a very short period of time, we want to bring it down to equilibrium. And also this heavier just below critical damping. And you can kind of see that when it comes down, right, it go past the x-axis. Okay, because it comes down too fast. It comes down too fast, so sometimes it's like overshoot a bit. Okay, overshoot, like not exactly they can stop at the equilibrium position. So when they come down too fast, sometimes they overshoot their equilibrium positions. That's why you have the graph like this. Okay, it goes to the other side and then come back, and then eventually it goes up to the zero line. Okay. All right, guys, I'm going to give you a 5-minute break, and then we'll come back, look at a few examples from the past years, and then I will give you exercise. Okay, so now is 7:57. We'll come back at 8:03. Okay. Okay, let's continue. Okay, we look at 3 examples. Example 1. Okay, so here on the graph, there are 2 oscillators, oscillator P and oscillator Q, that are vibrating. They have the same mass. And we want to find the phase difference. Okay, how to find the phase difference? The phase difference between the 2 oscillators. So phase difference is in angle between the wave number 1, the solid wave, and the dotted wave. Now, to find the phase difference, first is you want to find a similar point. Okay, find a similar point on the wave between the 2 oscillators. So let's look at the Q oscillator. Oscillator Q, let's just take the most obvious one. The easiest point would be the peak, the crest. Okay, let's call it point A. And another similar point, okay, you see that this particle, right after passing through A, it goes down, right? It goes down. And we want to find a similar one in oscillator P, which is over here also, because after this, it goes down here. So these 2 points are similar. We have also another point that is similar. Can you see which one? Over here, right? Here, particle also move down. So that means we got 2. Does that mean that we have 2 answers? Yes, answer is yes. We have 2 answers. Okay, let me show you here. Now, first we calculate point A and point B, this P. Let's call this point C. And let me explain why in a bit, why we have 2 answers, okay? So point A and point B, similar points. So we take the difference in time first. We take the difference in time. We kind of find the phase difference using the ratio, okay? So we use ratio, is that we find the difference in time over the time of one wave, that's one period, and equals to the difference in the angle over the angle of one period. Okay, that's 360. 360. Okay, so for these 2 points, we find this change in time. That means this is 1 point. Okay, what is this? 1.4 minus 1.2. Change in time, 1.4 minus 1.2 equals to 0.2 seconds. And we want to find the period. The period is the same between the 2 waves. T equals to, from here, we look at till here. So we have 2.4 and 1.2, right? So 2.4 minus 1.2 equals to 1.2 second. Put in here, 0.2 over 1.2 equals to change in angle over 360. And then we find that the angle is 60. That is the phase difference in terms of degree. So 60, you're going to change to radian times the pi divided by 180. You get 1 over 3 pi. 1 over 3 pi radian. That's the first answer. Okay, 60 degree phase difference between that 2 waves. Now another one is between A and C. That is also similar points. So the angle between this one would be, again, I use the same thing. This one over here. This one over here is 0.2. And this 1.2, right? So the change in time is 1.2 minus 0.2. That is 1 second. Period, I use back the same, 1.2 second. So I'm going to write it. Change in time, period. Change in angle, 360. Okay, so 1 second over 1.2. Change in angle over 360. So we find that this angle is 300 degree. This is also an answer. You have 2 answers. Why you have 2 answers? Because in mathematics, when we study angles, here, 60, from here to here, 60, there's another angle, right? There's another angle from here to here. That is 300. So that is what? That is the complementary angles. That is the complementary angles. So answer is 60 and 300. Now, especially in the objective, in the multiple choice question, sometimes it's tricky a bit because when students they found 300, but they find that okay, 300 is not there. It's not in the option A, B, C, D. There's no 300. So you have to know there's another answer. So you go and find the other one. That is the 60. Okay, because in the objective ABC, sometimes they show only one answer. They don't show the other one. Okay, so when you get something, okay, it seems like okay, this is not why there's no answer. Okay, you try to find the other one. That may be the answer here. Okay, so that is on finding the phase difference. Now that is for number one, and number two. The maximum acceleration of the oscillator. So you just use formula, maximum acceleration, A max. We know that A max equals to omega square amplitude. Right? So since we already know the period, then we just put in 2 pi over, period is 1.2, square times into the omega. Be careful with the unit also. Here, this one is what? 3 centimeter, so 0.03. Right, let's calculate this, we get 0.822 meter per second squared. That is my answer. Okay, example 2. A ball is given a small displacement and then release. The variation with time of the displacement of the ball is shown in the figure. Right, state 2 times at which the speed of the ball is a maximum. Right, so maximum speed, max speed, that means x is 0 at equilibrium position. Okay, so we focus on this point here. Now, oftentimes the exam, they won't give you exact point. They will give you like in the middle of the square. Okay, so you need to calculate this one. You seldom get like a very nice exact point, right? So this one, we want to find the time here, and in here, right? That is where the maximum speed. Okay, so then you need to do the scale. You have to be look at the scale. Okay, you see this one 0.4 minus 0. We take the difference. 0.4 minus 0, that's 0.4. And then there are 10 squares, we divide by 10. We get 1 square is 0.04. Okay, 1 square is 0.04. So we do 1, 2, 3, 4, 5, 6, 7.5. 7.5 times 0.04. You get 0.3 seconds. Okay, so that's the first one, 0.3 seconds. And the next one over here, this we started at 0.8. So we do 0.8 plus how many squares? 1, 2, 2.5. So 2.5 times 0.04. 0.9 seconds. Okay, if you want to find the third one, this one, we started from 1.2, so we do 1.2 plus how many squares? 1, 2, 3, 4, 5, 6, 7.5 times 0.04. 1.5. Okay, 0.3 and then 0.9. Oh, they only two. The maximum speed of the ball is approximately 0.08. So V max equals to omega r. Okay, so to get the omega, again, all the formula has omega, so you need to find omega first. Omega 2 pi over period, and period you can find from here, right? We can just take the 1.5 minus the 0.3. Okay, 1.5 is over here. Minus out this 0.3, we get the period of the wave. Okay, so 2 pi 1.5 minus 0.3. That's 1.2. So 2 pi over 1.2 times to the maximum, the amplitude, which is 1.5, 0.015 meter. 0.08 ms minus 1. Okay, we have one more, last one. Okay, example 3. The ball is free to oscillate along the straight line AB. Spring remains stretched, and the motion of the ball is simple harmonic. All right, use the figure to find the amplitude and the frequency. Okay, amplitude. Okay, but this one very easy. Just look at it. 1.7 cm. Okay, 1.7 cm. Frequency. Get the period. Frequency equals to n over t. Right. So you just find what is one. I can just start from the start easier because it's 0. The time is 0. So A, B. That's one oscillation. N equals to 1. And the time is 0 point somewhere here. Okay, again, you need to find what is this. All right, so again, we take the difference of the scale, 0.4 minus 0.2. So that's 0. You divide by 10 squares, right? 0.2, and then we divide again by 10. So 1 square is 0.02. It started at 0.2, so 0.2 plus 1, 2, 3, 4, 5, 6, 7, 8. 8 times 0.02 plus this one, we get 0.36 second. Okay, 0.36 second is this one, 0.36. So that means n is 1, t is 0.36. Divide this, we get 2.78. Two significant figures, so I just put it as 2.8 hertz. At the back, still got 2 more. And usually they'll ask you to draw. Very often they ask you to sketch. Okay, what is the time? What is the graph of acceleration against displacement? Okay, so we go to last page. Okay, show that the maximum acceleration of the ball is 5.2. Right, same with the first one. Max square r. We are given the frequency, so we use 2 pi f square r. 2 pi times 2.8 square times 0.017 in meter. And we get approximate 5.2 meter per second square. And then the last one is use your answer in A to plot, right, on the axis the variation of displacement of the acceleration of the ball. Now, how does your acceleration displacement graph looks? Here we have, okay, plot in 10 power of minus 2. That means our maximum amplitude, is 1.7 meter, sorry, cm, right? Cm. So we have this times 10 power negative 2. We just write here 1.0, and we can put 2.0 negative. Okay, so 1.0, 2.0. And acceleration, we choose a scale 5.2, right? So just take 5, easier, 5, 10. This is negative 5, negative 10. Okay, how does your graph look? At the max displacement, negative, the acceleration is 5.2 because acceleration is proportional to displacement. Okay, acceleration is proportional to x displacement. The larger displacement, the larger the acceleration. So that means at this maximum, this extreme here, it should be a maximum acceleration. So 1.7 somewhere here, this one. Okay, and the same on the other side. 1.7, 5.2. So your graph should look like this. This is the graph of acceleration against displacement. So typical graph here. Ax negative r, should get a straight line that has a negative gradient.